Okay.
Okay. Today we are going to talk something about approximate information using expectation propagation. And let's first see what's Bayesian paradigm. In a nutshell, Bayesian paradigm means you express any unknown with probability. You try to reason everything with probability. And the property of this Bayesian paradigm is that, for example, you have some for example, you have some data here, and you choose a model here, and you combine the data and the model together, and you can get the posterior distribution. And if you have some new data come in, and you have new data, then you just use this posterior as your prior and make new inference, and then you get your new posterior. And with your posterior distribution, you can do some prediction or decision or reasoning. So if you use Bayesian model, then you don't need the data if you get the posterior distribution. So you decoupled your data and your model. So given your data, you can train your posterior, and you have your posterior, you can do the reasoning and the prediction. And if you have new data, you just use your old posterior as a prior and get a new posterior. So it all comes from the Bayesian rule, something like this. Suppose X is some hidden variable unknowns, and you have some observation Y here, and we can use the Bayesian rule. Here is the joint probability of X and Y, and here is your model evidence, Py, and you can factorize the joint probability of Px times Py given X over Py. And the first term is prior, and the second term is likelihood function, and here is the model evidence. And for Py, you can take integrate over Px and y given x dx. Then you get your model evidence. So this is the Bayesian rule, and this is the Bayesian paradigm of Bayesian inference.
So here, model, where is it?
Where is the model?
Yeah.
Model is, for example, if you have some data and you suppose it was sampled from Gaussian distribution, then Gaussian distribution is your model. You can suppose your data sampled from other distribution. So this is your model. If your model fits your data, then you can get a very good estimation. Otherwise, it may be not a good one.
So in this in your example, the posterior distribution is for
the unknown. You can think about like this. You have some observation data, and it was controlled by some hidden variable, and you want to know this hidden variable. And in Bayesian paradigm, you reason it by estimate the probability of those hidden variables. This is your posterior. You do not estimate the hidden variable directly, but you estimate the distribution of that hidden variable. So this is different between the Bayesian paradigm and the other non-Bayesian paradigm, like maximum likelihood. In maximum likelihood, you give a bunch of observation, and you can estimate a hidden variable based on this observation. So this is a fixed estimation, right? A fixed estimate of the hidden variable. If you have new data come in, you should combine all your data together and make another estimation. right? If you use maximum likelihood, you cannot decouple your model and your data. Every time you have new data come in, you should involve all the data to make a new estimation. But in this way, if you have maybe you have a 10 number of data, you can calculate your posterior based on this kind of data. And you use this posterior like your prior if you have new data coming. So this is it.
There are more examples.
Yeah, there are more examples. So here's some properties of the Bayesian paradigm. So we got posterior distribution from the observation. So this posterior distribution is a summary of what you have learned from your data and based on the given model. And you have the posterior, you can make a prediction based on this test data. And it's very efficiently to incorporate new data as what I just said. And another property is it can avoid some extreme conclusion when testing data is not sufficient. Let me give you an example. For example, if you want to flip a coin, they have a head and tail. And if you, the first 3 times you flip this coin, you get 3 hands, right? So you have you have 3 hands here. So if you use the maximum likelihood estimator, what you get?
So the probability of having head is 1.
Yes, the probability of head is equal to 1. So this is not, if you use any common sense, you know this is very not extreme conclusion, right? It's not make sense. If you use the Bayesian paradigm, you should include a prior in your model. Then you estimate the posterior equal to the, not equal, maybe proportional to the prior times the likelihood. So this prior, maybe you see this, you know this coin is a fair coin, so the probability of head and tail are half-half. So in this way, the result won't be 1, right? Because you include this prior, maybe 0.5 times something. Yeah. So if you make more experiments, your result will be approach the true distribution, right? So I think, so what's the tools to do the Bayesian inference? And in this presentation, we use a fact graph, and the fact graph is a kind of graphic in the graphic models. And the fact graph just represents the factorization of a function. And suppose we have a function f, x, y, z, and it can be factorized as fa of xy, ft of yz, fc of xz. Then the fact graph provides a very useful and intuitive way to represent this factorization. So in fact graph, there are 2 kinds of nodes, the variable node and the fact node. So each variable node represents a variable in the function. So in this function, we have we have 3 variables. So we have x, y, and z. We use the circle to represent the variables, and we use square to represent the function. So we can write out the fact graph of this problem. So here is the FA, here is the FB, and here is the FC. So if we want to evaluate this function, we just simply make a product of all the factor functions. So this factor function provides a very useful and intuitive way to solve the factorization of a function. Right?
So how do I use it to represent the posterior?
Okay, because your posterior always has this form. For example, if you have a posterior like this, p by the px given y, x can be a vector and y can be a vector, right? And it's
So the posterior. So y is the observed data.
yeah, y is
X is your model.
Yeah,
the
your
parameter of your
yeah,
model.
Yeah, your model parameters. And it's proportional to the px, py given x, right?
Yeah. So first term is the probability of the parameter of the model.
Yeah.
The second one is likelihood of.
Yeah. And for the likelihood, we can further factorize it like I equal to 1 to n. Suppose we have n number of observations, and here y right. So we can factorize the likelihood term like this. So what's this? It's a product of many factors, right? So each factor have its own variables, and then we can represent the posterior by using a factor graph. Right? So factor graph provide a very useful and intuitive way to represent your posterior, and I will give you another example later. So here is the example, and suppose we have a Gaussian distribution and with a known mean and a known variance. We suppose the variance is 1 and the mean is mu, and we have some data like sample from this distribution, and given x equal to x1 to xn. So we have n number of observations, and this observation was sampled from Gaussian distribution with a known mean and variance plan. The problem is we want to know what's the true mean based on the observation. So this is our problem. So we can write down this factor graph like this. So in this problem, we see we have a parameter. The interesting parameter is mu here. So we write mu here. And if we want to use the Bayesian inference, we need a prior for the mu, right? So we have a prior for the mu, p0 mu. Here's a prior. And we have a lot of observations, right? So we have x1, x2, and xn. Fine. Good. We have the observation. And each observation was governed by the parameter, right? So we have a function here, a factor function here. Here the factor function is the pxi given mu here. So we write down the posterior given x equal to p not equal proportional to p0 mu. So this is a factor graph of this problem, right? Any question? No? Right. So we can evaluate this product of all the factors and get the posterior. And if we have this posterior, we can make prediction of mu, right? This is the distribution of mu. Maybe it's a Gaussian like this. So given this distribution, we can predict there's a mu.
Make prediction about mu or make prediction about next x?
Actually, you are interested in the mu here, and if you know mu, you can do everything.
Generate x.
Yeah, you can generate x, you can predict x, and yeah, everything. Yeah, actually, it should be predict the next observation. Yeah.
Actually, there's nothing for repeating the next observation for this model. Because it's so random, right? You give the mu, I don't know.
Yeah, I just
in this case, it's not exactly very interesting for the next.
Yeah, so
they are all
I didn't
random
see
interesting.
this predict the next observation, and then he asked if you
Yeah,
can, and I say
Actually, I want to answer like this question.
Yeah, because
this
it's
case,
random. Yeah.
this case is not very interesting. You know the mu, so what's the next observation?
Yeah,
The first
it doesn't
observation
make
is
sense.
a mu, right?
Yeah.
Just a mu. Right?
Yeah, if you
just
have
mean-
a
what can you predict for the next observation?
Yeah, I mean,
The basic best estimation is just mu.
yeah.
that's true.
Yeah.
If you consider another problem, it's a marker
For this
training.
problem,
Yeah.
it's not interesting.
Yeah, yeah. Okay, let's continue. And now we have two types. The first one is modeling. We choose a fact graph that can represent your data, and you choose your.
Actually, I have another question.
Yeah.
So the p mu in last slide,
Yeah.
where can you get the p mu?
P mu. Okay. If you have your model, then you know what's the distribution of mu, right? It can be a Gaussian, can be a Approximate, can be. You should choose your model first, right? You suppose your mu has some. First, you choose your model of your observation here,
Yeah.
and you want to make your problem is trackable. So you choose a conjugate prior of this likelihood. So this.
So the p mu, the model for p mu is assumed also.
No, the model of P mu is come from the likelihood function. You want to make your problem trackable, so you choose a conjugate prior.
So you have a.
You model just for your data. If you choose a model for your data, then it's reasonable to choose a conjugate prior for your
So
likelihood
you have
function.
one-to-one mapping.
What do you mean by that?
You choose function, you choose distribution, and then from this distribution you get a conjugate prior
Yeah.
for distribution, and then you assume the p mu to be in that distribution.
Yeah. Right. For the flip of coin, the likelihood function is a well-known distribution, so you choose maybe directionally or not directionally beta distribution as a graph. Right? So there are two tasks here, and we have a modeling. So we choose our model, and we choose a fact graph to represent your data, your model. Then if you have your model, you should make inference based on your model. So the algorithm to do it is exact inference. For the previous case, you can evaluate each likelihood and get a product of all the likelihood, then you get your exact posterior. But you can not always do it, because if your likelihood is very complete, then if you want to get the true posterior, it's very difficult because it's very expensive. I will show you an example later. And so in this case, we need some approximate inference. inference method. There are mainly two kinds of approximate inference method. One is the stochastic method, and the other one is the deterministic method. So for the stochastic one, is usually means sampling. You make sampling based on some distribution, and you use a particle to approximate your posterior. And the problem of the sampling method is very computational demanding, which means you need a lot of computational power to do it. But the advantage of the sampling method is it almost works for any integrate, which means your posterior can be in any distribution. It can be multi-mode and can be very compact. And so this is a stochastic inference method. Another one is the deterministic inference method, like EP or VB, variational Bayesian. In this method, it's very cheap in terms of computation, and because they do variational inference. And the problem, the disadvantage of this method is it only works for very simple posterior. Your posterior can only have maybe one unimode. It cannot be a multimode. Otherwise, you cannot use get a closed form solution for that. And let's consider a problem called the clutter problem. And y is the observation here. X is some hidden parameter. And the likelihood function of is given here, which means y was sampled from two Gaussian distribution. They have half time was sampled from here, and half time was sampled from here. So the likelihood function has this form. With half time was sampled from this distribution, and half time was sampled from this distribution.
If you add to a Gaussian, this is supposed to be another Gaussian.
No.
No, this is a mixture of Gaussian.
This is a mixture of
If you say 0.5 times this one plus 0.5 times that one, it sounds like a combination of two Gaussian.
No,
your combination of Gaussian is that you have two variable, they're Gaussian, and you are always adding that. For example, you have 100 variables sample from one Gaussian, and have 100 variables sample from another Gaussian. And if you, let's say the first one called x, the second one called y, and then you add these two x and y, and you call it w, and then this w will be Gaussian. But now it's not talking like that. We are talking like sometimes we sample x, sometimes we sample y. Like first instance we take x, let's say second instance we take y, and then the instance we take x again.
Yeah, I got what you're saying. So, but so it's like z. I mean, in graphical model, z like have an arrow to x can be a mixture of Gaussian or whatever. So z can be the vector choosing from each Gaussian. But here, I mean, if you add them together,
Well, it's adding the distribution. It's not adding the variable here. You look at the probability distribution is given by that, given by 0.5 and something 0.5, and it's basically a Gaussian, just a Gaussian profile.
so adding to distribution.
Yeah, we are not adding two variables, we are adding two distributions.
Yeah, I can give you another way to explain your problem. Yeah, let me consider something like this. And for example, py1 was sampled from the first Gaussian, right? And maybe py2 was sampled from the second Gaussian. And the probability of the first Gaussian was maybe we have another variable c equal to 1 equal to, and p c equal to 2 equal to 0.5, right? So how do you sample from a mixture of two Gaussian?
Actually, I get it. So you first choose a C.
Yes,
and
yes.
Depending on C, you choose different distribution.
Yes.
So
you first sample C, then based on C you sample N.
yeah. So actually, my question was, if I write in that way, so how can I distinguish between adding to variable to adding to distribution?
This is adding two variables, right? And no, this is adding two distributions.
Yes.
Adding two variables are what I said at the beginning, like you have x and y. Now you literally add them together. So each time you take x and take y and add them together, and this is w. And then you, at the second instance, also you take another x, another y, and you add them together. But in this case, it's basically the first time you probably get x because your c is equal to 1. And the second time you pick y because your c is equal to 2. And the next time maybe you pick y again because your c is equal to 2.
Then you draw a histogram of your sampling, then you get this form. So it's not add your observation, it's just get a histogram of your observation. Each point was sampled from only one Gaussian at each time.
I think I have no problem with this.
So, so what's the fact graph of this model? Let's see. So let's see the fact graph of this problem. We are interested in the hidden variable x, right? So we draw x here is the variable, and we need some prior for x. We choose Gaussian distribution for x because the magnitude is a mixture of Gaussian. And here is the prior here of x. And we have a bunch of observations here. It's mine. And each factor function is represent the magnitude here. So we want evaluate the posterior of x, right? Given by it's proportional to px times I equal to 1 and pyi given x, right? So here the magnitude function is a mixture of two Gaussian. So if we have 2 pyi given x, so how many Gaussians in posterior? It's 4 Gaussians, right? So if you want to do exact inference, you have 4 Gaussians in your posterior. So if you have n equal to 100 observation, so how many Gaussians you need to evaluate in your posterior? It's 2 to the n, right? It's exponentially increased. So this means if you want to exact inference for this problem, and you have 100 observation point, you need to evaluate 2 to the 100 number of Gaussian to get the posterior, right?
So is it all the data from the mixture of Gaussian the mix of two Gaussians. There are actually only two Gaussians.
Yeah, there are only two Gaussians. Yeah. So because your likelihood function have this form.
For each likelihood,
But
for each
for
observation.
first distribution, the mean is not fixed, is a zero mean, and the variance is 100. Because of this, you don't have exact two same distribution. The first distribution for each sample it can change. Because, for example, you can one time pick, for example, a distribution y x equal to 1 with the variance 1, and next time it can be something between, for example, minus 100 to 100. For second one, pick up from the first distribution. Because the mu of the first distribution is the x, the mu 0, and the variance is equal to 100. It's not the exact same distribution.
No, sorry. Here x is fixed. It's a known parameter. It's fixed. Suppose you have a machine and you know x, right? You know x maybe equal to 1, right? You have a machine, you know x equal to 1, and you just give out your samples to your audience, and you like your audience to guess what's your x. This is our problem. Because you don't want this problem very easy, so you add some noise. So it's here. So half time you sample your y from the true distribution, means x may be equal to 1. You know this number. And half time you sample from another distribution. You just want to confuse your audience, right? So Amy has a machine. He knows x equal to 1, and he sample y and give it to his audience. And half time he sample from the true distribution, like here x equal to 1. Half time he sample from another distribution. Just want to confuse your audience, right? And the audience receive all the information, all the observation, and make a decision. What's x in Amin's machine, right? So this is the problem. So this is why the likelihood has this form. So half time maybe from the first distribution, half time maybe from the second distribution. So your observation is y. So you don't know y comes from which distribution. So you suppose each distribution has half weight, and you put your observation in both of the distribution get likelihood. For example, if you have a very extreme condition like here, maybe 0.9 will sample from the first distribution, and 0.1 will sample from this distribution, and you receive maybe 100 number of observations. Then you make a histogram of your observation. So what's this? There should be some distribution like this, right? Because maybe 90% will sample from the first distribution. So if you want to make a guess, the x should be come from here, right? So this is the problem. So in this case, if you want to do exact inference, you should evaluate 2 to the n number of Gaussians. So it's very expensive and sometimes intractable. All right?
Well, I'm a bit slow, but I still don't get why there are not only 2 Gaussian, but 2 to the n.
Okay, let's expand. Suppose you have one observation, right? So you interest your posterior distribution. What's the if you have one, if you only have one observation here, your posterior has this form, right? This is your posterior distribution. If you have two observations, so your new, we use the one here, maybe two here. This is one observation. If you have two observations, so you use your posterior.
Two observation y.
Oh yeah, sorry. Yes, it's two. Yeah, you have two observations here, so you use your posterior as your prior here, right? This is the number one property of Bayesian inference, and times another plus 0.5 by 2 given 0.10, right? So if you want to make a second prediction of x, you incorporate another observation here. So in this case, you evaluate two number of Gaussians. So in this case, you evaluate another two. So how many products?
Four.
Four, 对吧？
Oh, okay, but actually you write it incorrectly here. P is given y2, P is given y. You're
Yeah.
multiplying the P is given y1 and P is given y2 here, is that?
What?
You need to, I mean, this doesn't work. You use the first equation is fine.
Fine.
This equation here is fine. You expect that, but this thing is not exactly correct. This is a vector here, right? Is that what you're referring to? Is that y is a vector here?
No. It's the second observation. Oh, yeah. Sorry. It's not.
Tracer.
Actually, you can just use this.
Yeah, but you can get the idea.
Yeah, you get the idea, but because it's on
notation is
tape,
the-
I don't want you to
Yeah, all right.
have mistake and I don't count it out.
Yeah.
So you can just look at that first equation is fine.
So each time you involve a new eigenvalue function, you should evaluate another Gaussian. So you have two times 2 is 4. You have n is 2 to the n number of Gaussians. Right? Yeah, I think another maybe.
Yeah, basically, you have 2 to the n so many terms
Yeah.
of multiple of Gaussian distribution. Remember, when you have multiple of this Gaussian distribution, they are Gaussian. Yeah. So basically, for example, you have like, let's say just 3 terms there, like three observations there. Then you have 8 terms there. Each of them a product of Gaussian, and that means that each of the product is a Gaussian themselves. So basically, you become a mixture of 8 Gaussian have different variants and different variants and different mean. Because your 8 of them, remember, when you mix them together, you have this multiple of this in some way, right? When you multiple this for 3 times, and you have this variance like 10, basically have like 3 times of that variance. And if you have this multiply 3 times and 3 times that variance, you just see. If you this multiply 2 times and this multiply 1 time, your variance like 12, for example. So each of them different variance, and also the mean will be different also. So therefore, like you have a mixture of Gaussians with different shape, basically.
A very stupid question. So can we assume the mean to be the same?
No.
Because
How can
y
we-
is different, your observation is different. So you consider x is your variable.
Actually, let's take a simple example. It's just two of them. Actually, maybe Shuang should be based on, just make a simple example. Let's say y is just, maybe y1 is 0, y2 is 2, for example, just two of this.
I just wrote the same example.
Oh, you wrote that one?
Yeah, I just wrote that one.
But are you using, let's say px is just
Equal to 1, then the second one equal to 2. You mean p1 equals 1, p2 equal to 2?
y1. Let's just put it 0, I'm not sure it will be easier.
Okay.
And then your px is here, right? Then you have 4 terms here. That when you multiply out the 4 terms is
Then you have 4 terms.
yeah.
Then 0x1 plus 0.5 and 0, 0, 10. This is the first active term times the second active term 0.12 times 1 plus 0.2. So there are two different Gaussian, right?
Maybe you just put one term first. Have you multiplied that yet? Okay, yeah,
Yes.
you're multiplying now.
So that you should evaluate full number of Gaussians.
Yeah, and this one, what's the mean for this one, for example?
The first, this mean is 0, right? The variable is x, and this mean is 2. If you consider
No, I
x,
guess, no.
what do you?
The mean should be, okay, let's ignore the pi now. Let's say the pi, I don't care about the pi. Then you have two, when you multiply these two, you have the observation. It's like one is 0, one is 1 way, one of them is 2 way. Actually, the mean should be 1 way, x1. If I ignore the pi, what I mean is that the mean is the mean of that x.
Okay. You can see.
Not this become a distribution of x, but y now is fixed. Just think of the distribution. This term says, yeah.
Minus x minus 0 over 1 times x minus 2
Oh, sorry, actually. Oh, yeah. Yeah,
over 1, right?
yeah.
So it's exponential something like x squared plus x is 2 squared, right? Something like this. So you rearrange this term, you get another Gaussian.
Yeah, then you complete the square. Then the mean should be 1, right? I mean, intuitively, it should be 1 because
Yeah.
the first observation is 0, the second observation is 2.
Uh,
Then now I'm trying to estimate x, then it should be the mean if you. But
Yeah, here's a formula to do multiplication of Gaussian. The mean is the first mean over first variance plus first mean, the second mean over second variance.
your variance is the same, right?
Yeah.
In that case, yeah. So then the mean is just equal to, and then,
It's not the average of mean.
yeah, but your variance are the same.
But the first variance is not the first variance is come from
But
here.
this is the same. This is both one, this is 1/2, this is.
Oh yeah, yes.
Yeah, I mean, it's intuitive, right? It's intuition, right? That's because you are having the same two distribution of the same variance. And then now I'm asking like, the first observation is basically 0, the second observation is 2, and now I'm asking you what is the
Oh,
mean
yeah.
for that x, of course it has to be 1.
Yeah.
But I just want to say if you elaborate that, given the observations and you want to estimate the x there, then if you just don't, now remember the observation is fixed, you can think of y is fixed. And then you're just trying to get the distribution of x there. Then if you have two observations, then basically you have like 4 terms there. And each of the term is basically have different mean and different variances for the x there, and therefore you have a mixture of four Gaussians. And if you have like p observation, you have a mixture of a Gaussians. That's all.
Is that clear? Okay. So let's continue here. So here is a comparison between the sampling method and the deterministic method. So if your posterior has a very compact fold and maybe 2 mode, then you cannot use this deterministic approximation method. So you can just draw samples according to some distribution, and you can get a very good sampling. That's the name. So if you use sampling method, it's guaranteed to get very accurate result usually. If you have a good sampling distribution, but the drawback of sampling method is it's very expensive. You need sample maybe 1,000 particles and several times, so it's very expensive. So the deterministic approximation method is very cheap, but it works only for very easy form posterior, and we can see a lot of problem has this very easy posterior distribution, because if you sum amount of random variables together, if you have enough number of observations, even each observation from non-Gaussian distribution, but if you sum them together, you will still get a Gaussian, because this comes from the central limit theory. So you have different observation from different non-Gaussian distribution. When you have enough number of sample observation, you get Gaussian. And in deterministic approximation method, there are mainly three of them. The first one is approximate approximation. They try to match the mode. You have a Gaussian, and you want to match this Gaussian to your posterior by match the mode. And the vibrational Bayesian try to match the lower bound. So people like this method because the vibrational Bayesian provides a lower bound for your inference. So it's guaranteed to work.
What's mode?
Mode means if you have 10 observations, the mode means for example, you have distribution. The mode means the distribution of x. The mode means the highest probability of x.
The peak.
The peak, yeah.
So the mean is the mode of Gaussian.
Mean is the mode.
Yeah, the mean
Okay,
of
For
Gaussian.
let's see,
Gaussian, the low and mean overlap.
Let's see here. Suppose you have a distribution here. What's the mode? Mode is here. Here is mode. This x give you your highest probability.
So if it matches the mode, does it also match the variance?
No.
Match the mean.
Only
No, for Gaussian.
And the second one is match the lower bound, which means you have a posterior here, and you will find a Gaussian that is the lower bound of this posterior. This means this algorithm will converge. So it's guaranteed to converge here. So this is the second method.
Excuse me, the match mode is just exactly the trivial
Natural.
match mode.
Match.
In the match lower bound, you said that one is the lower bound of the.
Yes, this is means
For the
you
match
are-
mode, exactly.
maybe only 1 point, not exactly, because your posterior can be here, and if you want to match lower bound, which means your approximate distribution always under your
This one is a match lower bound.
yeah. This
And for the match mode is.
match mode means maybe. Just make sure your mode, you have the same mode.
Oh, that's the peak.
Yeah, just the peak in the same position.
It's covered.
Yeah. Your Gaussian and your posterior, you want to approximate has the same mode. And the lower bound means your Gaussian is always under your posterior.
Actually, how
But-
sometimes it doesn't work like as much lower bound. For example, if your distribution is uniform, then your tail is just
Yeah, you should assume your the posterior is convex and everything like that. If it's uniform, then it doesn't work. And today we will talk the third method called expectation propagation. This one just want to match the mode.
So I was just thinking about what lower bound was. I mean, I still can't get the difference between this.
Okay. The lower bound means your approximate distribution always below your true distribution.
So the peak doesn't actually.
Your peak doesn't need to be there, right?
Yeah.
For example, I guess Shuang, you may try to draw something like little bit, I don't know, dwarf or like.
Yeah, something like this.
Yeah. So then.
Yeah, maybe you have here. They may be not the local minimum, maybe local minimum, but it makes sure your approximate distribution always under your true distribution. So each time you maximum your approximate distribution, you will gain something because it's a lower bound of that distribution. You try to iteratively maximum your approximate distribution by using this method until your algorithm converge.
So the peaks meet, or do they not?
What do you mean?
The peaks here. So do you actually achieve that?
Oh yeah.
Do you achieve that? I mean, you
you
get the
will
maximum.
achieve the local
Local maximum.
minimum. Yeah.
Okay.
Local maximum. Yeah. So today I will talk the third method is called moment matching. What that means is given a distribution like this, you try to match the moment. Here we match the first and the second moment. The first moment in Gaussian means mean, and the second moment in Gaussian means variance. Right? So we found a Gaussian with the same mean and variance of the posterior distribution. So in this case, here is the true here, and here is your approximate distribution. So this distribution is not your lower bound. It can be larger than your true distribution in this part, but the mean and the variance of this distribution is the same as this one. The same as the true distribution. I will give you another example.
So the true distribution can be any distribution.
Yeah, can be any. I just want to use a Gaussian to approximate. So we have three different ways. We can match the mode, we can match the maximum, the lower bound, and we can match the moment. So you have three ways to do it. So today I will talk the third way here, match moment. So this is mainly three different kinds of deterministic approximation method. So here is the moment matching with Gaussian distribution. here is your true posterior. It can be any distribution, and we try to use the Gaussian here to match the mean and variance. So the first moment is the first moment of your approximate distribution is here, and the first moment of your exact distribution is here. So we try to match them, so we said they are equal. So we want to solve this problem. If we solve this problem, we got approximate distribution which can match the mean and variance of the true distribution, right? So we match the second moment here. So this is the big picture of moment matching. And let's take another perspective of this moment matching method. What's that? What's the moment matching means? Actually, it means to minimize the KL divergence. What's the KL divergence is? For example, we use this as a example. The KL divergence is defined as this term equal to the Px Px or Qx dx. What's KL divergence? KL divergence is just give a measurement of the difference between two different distributions. They give you a measurement how difference between two different distributions. Let's see here is that if we write the KL divergence in another form. What's this? This is the entropy of X, right? And this is another entropy. It's not the exact entropy. It's another entropy of X based on the distribution Q, right? So this is means maybe this is entropy. Anyway, they need a minus sign in front, maybe here. We take a minus sign in front of them, then we brace here. So it's nice, but anyway, the entropy need a minus sign here, right? So this is the entropy of X here, and this is entropy of X given another distribution, right? So this is minus sign. So this is a difference between different entropy, between two entropy of X given the true distribution and the another distribution. So this is what KL divergence means. Just a measure.
You make it up.
What?
I mean, do you make it up or like?
No. I read some paper this time. That's another way to interpret.
Okay, at least the second term like is kind of heavyweight what you're describing. Because first one definitely is entropy,
Yeah.
but the second one,
It's
you
can
can say
consider.
like entropy, then it should be Qx multiplied by log Qx, right? Now this is kind of
It's the entropy of X given another. It's not exactly the entropy.
yeah.
Okay.
I don't think like it's good to say it's entropy at all.
Okay. It's not entropy. Okay. All right. Yeah, I just want to give you another interpret of the difference between the.
But I mean, this is very easy to show. It's basically KL divergence bigger than equal to 0.
Yes.
So, and you can see like only when your distribution is equal, then the distribution is equal, then it will be equal to 0.
Yes.
Basically, it's like a distance thing, but it's not really a distance because it doesn't satisfy stuff like triangular inequality or stuff like that.
Yes.
But it's basically kind of like a distance measuring distribution.
And the KR divergence is not symmetric, which means dQp is not equal to dPq. So here is the definition of dQp. So in EP we use this form of KR divergence, and in the variational Bayesian they use this kind of KR divergence. So in EP we try to minimize this KR divergence. I've also you minimize this kind of KR divergence is equal to the moment matching. And if you minimize this kind of KR divergence, it's equal to the method used in variational Bayesian. And here is an example. The moment matching is Gaussian is equal to the minimization of KR divergence in this form. And suppose the approximate distribution has this form. It was governed by hidden parameters. Suppose this is a Gaussian distribution here of your approximate posterior distribution, and theta is the parameter of distribution. So Gaussian is mean and variance, and we take an integral over x of this distribution. It should be equal to 1. And now we try to minimize the KR divergence PQ here with respect to the parameter state. And now, okay, let's see here. If we want to minimize this, we just write out both this is the integral of x of px dx.
By the way, px is a posterior distribution, right?
Yeah, all right. Px is your true posterior distribution, and qx is the approximate distribution. You want to match your approximation and the true. And this is log qx given the dx. So this minimization is with respect to state. So this is a constant. We don't need it. We just need to minimize this term, right? And I will show you. So if we want to minimize this, we just take first order derivative with respect to mu and v and set them equal to 0. Then we solve the equation, we get the result, right? So as we see, what's this? And here is the px has qx given z as the form over and we want to minimize the function px of qx dx, and we plug this qx given z into this integration, then we get px of 2 pi z, and here this term we got 1 over 2, right? For the first term, we take logarithm to this one. Then this is the first term, and for the second term, we get px x minus mu So there's a minus sign and there's a minus sign, so we have a plus sign. And we take a first order derivative of with respect to mu. So this term will vanish and
Excuse me, first integral is over x.
yeah, it's integral over x. And for the second term, we take a derivative with respect to mu. We get p of x times 2bx minus mu times 2, yes, right?
After square,
No.
it just x minus mu, your square should be gone. Oh, you haven't finished it. I thought you. But you are taking the derivative already, right?
Yes. We take first of the derivative of this term, we got this term, and the side is equal to 0, right?
Is it minus?
What?
Is it minus?
No. Because here is a minus and here is a minus, we got plus. And we take first of the derivative with respect to mu, we get this term. So what's this term? It's a px. Px is equal to px into px, right? Because we suppose v is not equal to 0. Then what's this? Mu is not a function of px, right? And we know px is a distribution, so px dx equal to 1, so we get 2 mu. So we conclude that mu is equal to px dx x. What's mu? Mu is your mean of the approximate distribution, right? So this is the moment measure of mean. It's just equivalent to the mean minus the scale divergence. And we see the variance. And we write out the variance. The form is something like this. 2 pi 3 plus px 2b 2x minus mu dx. Right. This is a PR diversity PQ. And we take first of all the derivative with respect to v this time. What do we get? Is the 2 pi b, right? And 2 pi here. We take a mod. We take the derivative with respect of mod. We get this denominator, and we take derivative of this inner term, we got 2 pi here. And we do it here. What do we get? This square, right? And change this side to a minus sign. Right? And we set this term equal to 0. And what do we get? Is we multiply by v square, 2v square on both sides of this equation, and we get this terms cancel, and p multiply the 2 times v square on both sides of the equation to get this form. So what's this? Is the v, right? And it's equal to px x squared minus 2x mu plus mu squared dx. And
that is
Variance.
the definition of the variance.
okay, yes. But this is not the second moment. I want to show you it's the second moment.
Oh, okay. But that isn't that is already the variance already?
Yeah, it's already variance, but we want to moment match. We want to match the first moment and the second moment.
But isn't that this one already show that the variance is the same as the v?
Yes, yes. So
If
you got the idea.
For Gaussian, if your mean is the same, variance is
Yes,
the same, then
yes.
everything is the same.
Yes,
Then all the moments will be the same also.
yes, yes. So we can.
So I guess we
skip
can
that.
skip
Yeah.
that.
Yeah, we just skip that. Okay, let's recall the counter problem. We want to estimate x given a bunch of observation line here, and
But by the way, like this is only showing like for Gaussian. How about other distributions?
for other distribution, if your distribution was from exponential family, then the definition of exponential family is qx equal to gz hx exponential z times mu of x. This is the definition of exponential family. Here z is your model parameters and u is your variables. And for Gaussian, the ux is x squared and x. And the state, you can match by yourself. I cannot remember that. But anyway, if you can compare this formula with Gaussian, you can get each terms here. And if you match the exponential family in KL divergence, you will get the px of ux dx is equal to the qx of u dx. So this is a general form. If your approximate distribution comes from an exponential family, so the minimization of KL divergence means the matching of your sufficient statistic between two different distributions. So you can prove it if you like. But for Gaussian case, it's just match the first moment and second moment. So this is why they call this method moment matching. So for non-Gaussian, yeah, it's not first or second moment. It depends on your UX.
They are matching the sufficient statistics.
Yes. Okay, let's recall the counter problem here. You have a bunch of observation line here, and you want to know the hidden parameter x. And the x has the prior here, and then I conclude the function like this term. And if we want to use approximate inference, we need to choose the Gaussian to approximate this magnitude. If we can find the Gaussian that give a best match of the magnitude, then we can evaluate the posterior within Gaussian. So there's no more mixture of Gaussian, it's just a product of Gaussian. So we solve this problem. So this is where the approximation comes from. We use a single Gaussian to approximate a mixture of Gaussian. So how is it possible? So let's see, this is a mixture of Gaussian. How can we choose a single Gaussian to approximate this mixture of Gaussian? If we do the KL divergence minimization, your approximate distribution just simply moment matching line. It's something like this. So it doesn't make sense if you choose your approximate distribution here, because your true distribution here is equal to 0. Doesn't make sense. So how to make this method make sense? We introduce the prior. And here's an example. Suppose the blue curve is the likelihood function. And if you don't have any prior information, if you minimize your KL divergence, what do you get? You get the blue curve, right? The green curve. But if you have a prior distribution here, you know your prior is here. What's your exact posterior? It should be here, right? If you know your prior is here, why not make approximate your green curve here? If you can make your approximation here, not match the whole likelihood function, just a point or a spot of your likelihood, and then you multiply your approximation with your posterior, with your prior distribution. You can still get a good approximation to the posterior distribution, right? The problem is that if you don't have any information, any prior information, you just want to minimize the KL divergence, you got the green curve, the green curve here. But if you know your posterior is here, you know your likelihood prior is here, then you can make an approximation here. Use this into Gaussian to approximate this mode, and then use this approximate times this prior, then you can make very good approximate to your posterior. So this is what I have taught. If you know your prior is here, why not make approximate here? If you make an approximate here and then times your approximate with the likelihood, then you get a very good approximate posterior. So I will talk how to choose your approximate distribution so that they can incorporate the prior information into the likelihood function. If you involve this prior information into likelihood function, then you know how to choose your approximate, not make a naive approximation like this, right?
So in the first figure, next slide. So the blue one is exact.
Yeah. The blue one is exact. Likelihood. And this blue one is your prior. If you times prior with your likelihood, you get your exact posterior like this. Yeah, we can see. This is your exact likelihood, right? This is your prior. If you times prior with the likelihood function, you get your exact prior here, the exact posterior here, the blue curve here. And if you make an approximation without any prior information, the best approximate is here, right? The green curve. If you times this green curve with this prior information, you get your estimation here. So this approximation is not good approximation, right? If you compare with the true posterior. This is because you didn't use any prior information in the approximation. Because you choose this green curve without using any prior information. So the best curve you can use is by using moment metric just match the mean and the variance, then you get this green curve. right?
Yes. In next slide.
The next slide is if you know your prior is here, why not choose approximate distribution here? This is a chicken and egg problem. If you know your posterior is here, no. If you know your prior is here, then you can choose approximate distribution here, right?
The blue one, the first blue one is so next slide please. The informed case, the blue one is
The exact likelihood.
exact likelihood.
Yeah. The other thing, because in the second figure you cannot see the other part of the blue one because we choose the green one that exactly match the second part of this blue one.
Oh, okay.
Because they are all Gaussian, so
It's still there, the blue one.
yeah, it's still there just under the
Okay.
green one. So if you know your prior is here, then we just simply choose the Gaussian match this part of your untitled, right? Then if you times this approximate with your prior, then you get a very good approximate posterior, right?
So use prior twice.
Not twice, once. What do you mean?
So in the first informed figure, you, according to the prior, you choose the approximation as a grade.
Yeah, in this sense, it's used twice. You first to know where is the prior, then you choose the approximate. Then you have your approximate is the prior, then you get your posterior. So I will show you how to do it. Suppose here is I can do functions f(i) of x, and we have some prior information here because q not I of x. This is a prior information. So here fi of x can be any distribution. It can be a mixture of Gaussian. And q not I x is a Gaussian. And we want to find Fix tutor, which is Gaussian. So that the approximate posterior very close to the true posterior, right? This is the problem formula of the previous slides. Right? So how can we do it? If we can choose here is the graph, here is the approximate distribution. How can we find this distribution, this approximate distribution? We use moment matching. Suppose here is your Qx, is the approximate posterior, and then here is the Px, the true distribution. We minimize the KL divergence between P of x and Q of x. Right? Then we found the posterior distribution. And how to get f, tutor of x. We introduce the projection operator here. This projection operator means we perform minimization of KL divergence.
So for the first figure, how do we select the right half of the distribution to approximate?
Okay. You mean how you tell the
Yeah, how to get this mark?
okay. Because if you evaluate this term, right? This is your true posterior, right? If you evaluate this term, what did you get? If you evaluate this term, it's only the right part, right?
Can you explain?
Okay, get a little bit lost also. So which one is your posterior? F is your posterior, right? Is that
You mean posterior? There are two posterior and approximate posterior. Here is the prior. Here is the likelihood. So you multiply prior with likelihood, you get your posterior.
okay. So which one is like higher now, Q or F?
Q not I is a prior.
Okay, Q is higher, F is likelihood now?
Yeah, F is likelihood. We found approximate likelihood function and tutor as a single Gaussian to approximate the mixture of Gaussian. We just we do not match each likelihood function. Instead, we match the true posterior and the approximate posterior. This is the trick. Because you multiply your prior with your likelihood function, you will only get to the right part. Because you suppose your prior is a Gaussian, right? If your prior is Gaussian here, then your likelihood function can be in any forms. But if you multiply your prior with your likelihood, you can only get a single mode here, right? Is that clear? You have a prior here, and you can have any likelihood function here. Because your prior here, so your distribution only pick this region, right? Because in the other region, the probability is equal to 0. If you add those two functions together, then you get.
Yeah, I guess the question is where do you get the prior there?
Where do you get the prior?
Yeah, when you P.
It's from here. Your prior is from here. You always choose prior from exponential family so that your problem is trackable.
Okay, so actually,
Because
in your figure here, I thought like, because I thought your previous figure here, you said like this is your posterior, but it's not really your posterior, right?
I never
it's
see
just
it.
the likelihood.
Yeah, it's likelihood. I didn't see it.
Oh, okay. I don't know. I remember you said it was posterior.
Yeah,
Because you said that you're going to match the. I asked you whether that one is posterior, and you were trying to minimize the KR divergence of P and Q, and then I asked you what is P, or like is P is the posterior. And
Yeah, P is a posterior. They always match posterior.
Yeah, but yeah, then actually here if I therefore this is not posterior. This is just like.
Yes, so we need to multiply the prior with mapping to that posterior.
But this is just like.
Yeah, this is not.
If I try to use scale divergence to apply on this as posterior, of course I'll get this.
Yeah,
But
yes.
actually this is just like and then you say you're going to multiply that with the prior, therefore the posterior is actually that.
Yeah.
And then like
I just gave you an example here. If you don't use your prior, your estimation is very bad.
yeah.
This is just an example to show you if you don't use your prior, then the approximation is very bad. If you use your prior information and you try to minimize your posterior, then your approximation is very good.
Does your prior change
Yes.
in EP?
Yes. Because the prior comes from the Q
previous.
node I. Yeah, the previous state. Any questions in that? Another thing I need to mention is why we choose the prior is the Gaussian. Because we have said, according to the central image theory, if you add enough number of observations together, you will always get Gaussian. Although each random variable is non-Gaussian. So it's reasonable to say the prior is Gaussian because you are thinking about the problem as a lot of observation. If your problem only have 2 observations, then and you still want to use EP, then you won't get a good result. This is
Can you use T distribution?
student T.
Yeah, because if you have limited number of observation, it will has a high variance. It's T distribution. Well, I'm just wondering. So
It's exponential, something like that.
T is from T squared. And T squared is from gamma.
I don't know.
I think you can try. I'm not sure. I never considered about that problem. Yeah, I cannot answer this question. And I see the other problem here. And we suppose the prior has this form. This has a very large variance. So x can be from maybe this is 0 minus 3 sigma. So this is very large variance prior. So it makes sense, right? So x can be from minus 300 to positive 300. So it's not a strong prior. Right? And we didn't do any strong prior here. And here's the eigenvalue function. And the problem is we want to approximate each eigenvalue function with approximate distribution by using single Gaussian. We do not directly match each eigenvalue with your approximate distribution. Instead, we match the posterior distribution, the approximate posterior distribution and the true posterior distribution. So this is how EP works. And then we can get to the approximate posterior, just simply a product of all your factors. It's come from the factor graph, right? And with some normalization constant. So I see the factor graph here. Here is the variable. Here is the parameter you are interested. Here is the Qx, your prior. And here is the Qi of x. And here is the observation yi. There are a bunch of observations here. this is a fact graph. And Pi is the true likelihood function for this factor graph, and for this factor function, and Qi is the approximate distribution of this true likelihood. And there's a Q naught I. Q naught I is from here, from other observations. So we multiply all these terms together. The message from other nodes, we got Q naught I here. So this is the Q naught I comes from. Because we have a lot of observations, so Q naught I is Gaussian according to the central limit theorem. Right? And we got Q naught I, then we can do projection, right? It's a Qi of x, Q naught I of x. We match by projection. If we use the projection operator, then this equals not approximate, right? So this is the new posterior.
You're missing a tutor somewhere, so Qi. It's the first one have a tutor.
Oh yeah, the first one we use F tutor to approximate F. In this case, we use Qi to approximate Pi. So we changed the notation. There's no more tutor here.
Qi to approximate Qi.
Yes.
Okay.
We changed the notation. We just want to make the notation consistent. Because we use approximate posterior and Qx, so we use Qi of x as the approximate likelihood. So this is the Qx, right? So this is the Px. We use the projection here, and we minimize the PR divergence, then we solve this problem. And here is a summary. And this is how we get the Q naught I.
Again, which one is prior? In this case, Q naught I.
Yeah, Q naught I.
Q naught I is the prior. So then Qi is the likelihood now.
Qi is the approximate likelihood,
Okay.
and the Pi is the true likelihood. Yeah. Here is a summary, and we try to first we get Q naught I by dividing the Qi of x from the approximate posterior distribution. We get Q naught I according to the vector graph. Then we perform moment measurement to update the Qi x. We get a new posterior distribution. This is an approximation of the true posterior distribution by using the projection operator. Here the projection operator just minimizes the two distribution. Here is a Gaussian. It's a single Gaussian here. And here is a mixture of Gaussian because this true magnitude is a mixture of Gaussian. And we use the moment measurement here. We got the new mean and the new variance. And we use this new mean and the new variance divided by the prior. We got the updated approximate distribution. And so this is a big picture of EP. And the following is some just show some details how to do the cluster problem. Due to the time is very late, so we can skip this. And if you are interested, we can talk about it next time. This is just show you how to. You see here, we only give you the equation here, the mu and the mu variance is the moment matching, but I didn't show you how to solve this integral, right? The following step is just show you how to solve these things, and just some details, and I think all of them get the big picture, and so you can leave this. So any question?